Let's start our lesson today from what we finished with last time. Last time, we just finished section 1, which talked about heat and work and the relation between them. And to summarize what we have last time, we can just watch the next video. Okay, these are three videos that show that we have three things last time talked about. Let's start with the
An
first.
isovolumetric process is a thermodynamic event that takes place at constant volume so that no work is done on or by the system. An example of this process is what happens inside a bomb calorimeter. A small quantity of a substance undergoes a combustion reaction, releasing energy and increasing the temperature and pressure of the gaseous products. The walls of the container are very strong, so there is no change in the volume of the gas. The energy is transferred only as heat.
So this is the first one, which is isovolumetric. No change in the volume of the gas. Okay, so iso mean, as I told you before, isolation mean separated it from the environment.
Now we will consider a process in which temperature is held constant. The word for this is isothermal. A close approximation of this process is if you were to carry a sealed balloon up the stairs of a very tall building. Since the air pressure drops gradually at higher altitudes, the balloon will expand. The balloon is growing even though there is a pressure force pushing inwards against it. Therefore, the balloon does work and it should lose internal energy. If nothing else happened, the balloon would cool off because of this. However, since the temperature of the outside air is warmer than the cooling balloon, energy enters the balloon and keeps the two temperatures identical. Therefore, the balloon neither gains nor loses internal energy. The energy transfer and work done are simultaneous, and so the process is isothermal.
So we have here the isothermal as the balloon idea, which we go with for high building. Number 3.
An adiabatic process is a thermodynamic event during which work is done on or by the system, but no energy is transferred to or from the system by heat. Consider inflating a balloon very rapidly. There is no time for energy to be gained by the gas in the balloon. The internal energy of the gas decreases because the balloon did work while expanding. Adiabatic processes usually happen quickly or inside well-insulated containers.
So this is the third one, which is adiabatic system. Now this all what we have last time, a summary for what we have last time. Now let's go for what we will have today. Now let's start with section 2. Section 2, the first law of thermodynamics. First law of thermodynamics. Of course, the word thermo, or the part of the word which called thermo, mean heat, and dynamics mean motion. So thermodynamic is a law that talk about the motion of energy or heat. First thing, how the first law of thermodynamics is a statement: energy conservation. Energy conservation means the changing of energy from one form to another, like changing heat energy to kinetic energy and vice versa and so on. Number two, calculating the heat, work, and the change in internal energy by applying the first law of thermodynamics. Number three, we will do the first law of thermodynamics to describe the cycle process. Now let's start. First, let's talk about the energy conservation. As we know, friction is a force. So here, if friction is taken into account, mechanical energy is not conserved. The energy conserved if there is no friction or air resistance. Like for example, if I throw a ball upwards, the ball going upwards, the potential energy increase and kinetic energy decrease and mechanical energy remain constant. This only if there is no air resistance. Also, when the ball going downwards, fall downwards, the potential energy decrease and kinetic energy increase to keep the mechanical energy remain constant. But with the air resistance and friction, there will not be mechanical energy conservation. That means the mechanical energy will not remain constant. It will change due to the loss of energy by friction force or air resistance. Another example, roller coaster in the amusement park. You know, roller coaster, that a car that we ride in and it takes us along a track that's going up very high and going low, then very low. This roller coaster, which is very exciting, is example for the mechanical energy and conservation. The steady decrease in the car total mechanical energy occurs because of the work being done against the friction. We know that the roller coaster car has a friction between its wheels and the track. This friction decreases the mechanical energy that the car has, okay? Between the car axle and its bearings and between the wheel and the coaster track. If the internal energy for the roller coaster and the energy dissipated to the surrounding air, the environments are taken into account, then the total energy will be constant. So if there is no friction and the energy is only inside the roller coaster, its parts, in this case, we have energy constant and remain conserved. Let's take a look for the example of roller coaster by video.
The total energy in a closed system is all.
Before we start the video, down here, at the top here, you will see the roller coaster car, and the red line is the track, going up and going down many times. At the bottom here, we have three rectangles. Each one explain the change which happened to kinetic energy, potential energy, and internal energy. So let's watch this rectangle while the roller coaster moving up and down and see what happened and what change happened to these energy at the same time.
The total energy in a closed system is always conserved, although it may be converted into other forms. While this roller coaster car is being raised up, energy is being added to the car from an outside source. This is not a closed system. The potential energy gained is shown by the red bar on the graph. After the car is released from the top of the hill, we will assume that the only source of friction is at the axles of the roller coaster wheels. Since nothing is adding or taking away energy from the car, it can be considered a closed system for the rest of our example. As the cart goes down the hill, its potential energy is converted into kinetic energy. Kinetic energy is shown by the blue bar. Gradually, friction at the axles causes heating. This change in internal energy is shown by the green bar. By the end of the run, most of the mechanical energy has been converted into internal energy. At all times after the first hill, the total energy remains the same.
So from this video, we saw that at the first hill only, we add energy from outside to raise the car to the top of the hill. After that, the rest of the track, the car just losing potential energy to gain kinetic energy and vice versa. Because of that, going up the first hill only is not a closed system, it's open system that lose and gain energy with the environment. But the remainder of the track, it's a closed system. That means the internal energy starting by the end of the first hill, the internal energy will remain constant by converting between potential and the kinetic energy. One of them increase, the other decrease, and vice versa. Okay. Now let's go for this, show you again what happened. In the first part, from A to B, we add energy. The energy added here is from outside, and this is make the car is not a closed system. Until it comes for the higher part, which number B, it is having the higher potential energy, because potential energy increase and decrease due to the high. Increase by increasing high, decrease by decreasing high. So the number B or the point B have the high potential energy. And at the high potential energy, the object stops moving before it starts the motion. In this case, there is no kinetic energy. Okay? After point B, the object released, so it moved easy without any external force. In this case, while it go down, potential energy go down and kinetic energy go up. To keep the total of them, which is internal energy, constant. So the rest of the track, when the car go up, potential energy go up and kinetic energy go down. When the car go down, potential energy go down and kinetic energy go up, and so on, to remain the internal energy constant if there is no friction. The principle of energy conservation, which means that the internal energy is constant all the time if you don't lose energy. That take into account a system's internal energy as well as work and heat is called the first law of thermodynamics. So energy conservation, which talk about heat, energy, heat, and work and energy, internal energy, this called the first law of thermodynamics. So we will talk about transfer of energy between objects due to losing work or energy or heat as the first law of thermodynamics. First law of thermodynamics can be expressed mathematically by a simple equation which equal delta U, internal energy, change in internal energy, equal Q, the transfer heat from or out from or to the object, and W, which is the work.